In the previous lecture, we discussed 4 different types of acid-base titrations where we were pretty much simply interested in how many milliliters of titrant does it take to reach the equivalence point, and can we detect that equivalence point with an indicator, a color change? Well, it's often advantageous to, instead of using an indicator or in addition to using an indicator, to actually track the pH in the flask or beaker as you add titrant all the way to the equivalence point and actually beyond the equivalence point. And if you do that and plot the results, you have what's called a titration curve. In this part of the lecture, we'll look at the titration curve of the titration of a strong acid by a strong base. You'll recall from the previous lecture the titration of 25 milliliters of the strong acid perchloric acid by 0.1219 molar sodium hydroxide. And we learned that it took 19.5 milliliters of this titrant to reach the equivalence point, that is to exactly react initially with all the perchloric acid that was initially in the flask, that the original concentration of the perchloric acid, which we could find once we knew how many milliliters it took to reach the equivalence point, was determined to be 0.09508 molar, and that the products of the reaction, sodium ion, perchlorate ion, and water, would be expected to give us a pH equal to 7 at the equivalence point. Now, if we use a pH meter during our titration and actually monitor the pH after each small addition of titrant, we can plot a titration curve, and for the titration of this strong acid by strong base, in this particular case, the titration curve would look like this. So what do we have? We have pH, which we're measuring with the pH meter, plotted on the y-axis, and the number of milliliters of titrant, in this case milliliters of sodium hydroxide, on the x-axis. We have the data in tabular form over here. So for example, we said the equivalence point was reached when we had added 19.5 milliliters of sodium hydroxide and that the pH was 7, and I've highlighted that point on the titration curve. Let's look at this titration curve in a little more detail. What we'll do is look at the pH in the flask at 4 key places in the titration curve. I call them regions. One of the things we'll do is add a column to our table which shows the total volume added. So in the flask to start with, before we've added any sodium hydroxide, when we've added 0 sodium hydroxide, the total volume in the flask is 25. After we've added 2 milliliters of sodium hydroxide, the pH goes up slightly, but at that point we have a total of 27 milliliters in that flask. This total volume, tracking it, will come in handy. So what are the 4 places that will highlight how to determine, or how the pH, how to defend these pH values at 4 different places? One would be the initial pH, that's before we add any titrant. The second would be the pH in the region between the initial pH and the equivalence point. There's nothing magical about this point that I chose here. We could have chosen the one at 10 milliliters, but I chose the one at 13 milliliters of added titrant. We'll look at the pH at the equivalence point, which we know is 7, but we'll look at that in a little more detail. And something new here from the last lecture, we'll be concerned, or at least look at, the pH in the region beyond the equivalence point. So at the equivalence point, we've added enough titrant, sodium hydroxide, to complete the acid-base reaction. After that, we just keep adding it, and we find that the change in pH with added titrant levels off, and I've picked this point to look at in the next few slides. So in these next few slides, we're going to try to show why we would expect to observe these pH values at these 4 specific points. First, it's always good to count how many perchlorate formula units are in the original 25 milliliters of solution in the flask. In other words, let's count our analyte formula units before any addition of titrant. And that's straightforward. We take the concentration times the number of milliliters, and we see that there were 2.377 times 10 to the minus 3 moles of perchloric acid in the flask initially before any addition of titrant. And since perchloric acid is a strong acid, what we're starting out with in the flask, in this case, is 2.377 times 10 to the minus 3 moles of hydronium ions, the same number of moles of perchlorate ions, and of course, water. Well, let's look at the initial pH. We say it's 1.02. How would we get that? Well, the flask, remember, initially contains 2.377 times 10 to the minus 3 moles of hydronium ion in a volume of 25 milliliters. That's the total volume in the flask before we add any sodium hydroxide. So the concentration of hydronium ions is 0.09508 molar. The pH then would be 1.02. This seems pretty straightforward. How about the pH after we've added 13 milliliters of titrant? Well, let's calculate that pH. We say it should be 1.68. How would we get that? Well, when you've added 13 milliliters of sodium hydroxide, you will have added 0.0015847 moles of hydroxide ions, volume times concentration of the titrant. Remember, the added hydroxide will react with hydronium ions that are in the flask in a 1-to-1 ratio to produce water. So how many hydronium ions will remain in the flask? Well, we initially had 0.002377 moles of hydronium ions. We're going to destroy 0.0015847 moles of hydronium ions because that's how many moles of added sodium hydroxide, which means the number of moles of hydronium ion remaining in the flask at this point in the titration is 0.0007923. Now we just get the concentration of those hydronium ions, the number of moles that are left, divided by the total volume in the flask. We get a concentration of hydronium ions from which we can calculate a pH. And we see this pH 1.68 in the table and on the titration curve. Well, now we've reached the third point that we've chosen to highlight, the equivalence point. Yes, we know the pH is 7. Let's look at this in a little more detail. You recall that this example, which was covered in lecture 3, it was example 1, is that it took 19.5 milliliters to reach the equivalence point. I just want to point out that sometimes we've been a little cavalier with our terminology, since When we described this in the previous lecture, technically what we found was that the student found that it took 19.5 milliliters to reach the endpoint, where we saw the indicator change color. And of course, we're assuming that the difference between the endpoint and the equivalence point is negligible if we were really clever about picking out an indicator. In any event, we could find the equivalence point by not even using an indicator, by just looking at the titration curve. What we would want to do is estimate the midway point of this steep rise in the pH. Now, technically speaking, how you would find that midpoint, which is actually mathematically an inflection point, would be by plotting the first and second derivatives of the data. We're not going to do that. We're just going to try to estimate it by looking at the graph, the plot, and estimating the midpoint. The equivalence point volume at this midpoint on the x-axis is 19.5 milliliters, and the equivalence point pH is 7. Now recall that we expected this pH because the products of the reaction at the equivalence point, sodium ion, perchlorate ion, are neutral, and the titration curve is consistent with that expectation. Well, how about our fourth point? This is when we've continued to add sodium hydroxide beyond the equivalence point. In other words, we've reacted all of the perchloric acid or all of the hydronium ions that were initially in the flask. So after the equivalence point, the original acid here has nothing to say about the pH. It's totally controlled by the number of moles of excess titrant that we've added beyond the equivalence point, and of course the total volume in the flask. So what we'll do here is calculate the pH after addition of 24 milliliters of sodium hydroxide, which would be 4.5 milliliters beyond the equivalence point. Well, how many moles of sodium hydroxide in total did we add? Well, we've added 24 milliliters times the concentration. So in total, at this point, we've added 0.0029256 moles of hydroxide. Now the excess hydroxide would be the total number of moles added minus the number of moles of hydroxide needed to reach the equivalence point. And this would be the excess right here, 0.0005486 moles of hydroxide, the excess hydroxide left in the flask. The concentration of that excess hydroxide would be that many moles divided by the total volume at this point. And then we can find the pH, technically the pOH, and then the pH, 12.05. Well, there's no reason why we couldn't add an indicator. And I think previously in lecture 3, we tried to defend our choice of indicator by saying if you ultimately look at the titration curve, you can see why these indicators that we picked out would work. Again, if you actually take the data and plot a titration curve, you don't need an indicator. But here we can justify why the indicators we chose before would probably work. Remember, what we want to do is pick indicators that minimize our titration error. It might be good to formally define what we mean by titration error, and the titration error would be the titrant volume that you've added at the endpoint minus the titrant volume at the equivalence point. That would be the titration error. And we want that to be at a minimum. In the previous lecture, we noted that both bromethymol blue and phenolphthalein would be acceptable indicators. We seem to lean toward phenolphthalein, even though the phenolphthalein color change was not where the equivalence point is. You can see bromethymol blue is better positioned. However, we deferred to phenolphthalein because we said visually it's a lot easier to see no color turning to a color than it is from one color turning to another. And we further defended phenolphthalein by saying, look, the pH changes so rapidly in this part of the titration curve that the difference between the volume added here and the volume added at the equivalence point on the x-axis is negligible. In other words, there's minimal titration error. So we can successfully use phenolphthalein, and the phenolphthalein endpoint we consider to be so close to the actual equivalence point that we don't worry about any small titration error.